All right, so the next problem we want to do is problem 26 from chapter 11. At the instant, 2 kilograms, so the mass of the object is 2 kilograms. A 2 kilogram particle P has a position vector R of magnitude 3 meters, an angle that's 45 degrees, that's your theta 1 here, and the velocity vector v has a magnitude of 4 meters per second, and angle here is given, that's 30 degrees. A force is applied, has a magnitude of 2 Newton, and angle that's 30 degrees, acts on the particle. All 3 vectors lie in the xy plane. About the origin, what are the magnitude and directions of the angular momentum of P? So you also find the angular momentum, of P about this origin. Okay, that's your reference point, and also you are asked to find torque on this object because there's a force and there's a moment on, so there's a non-zero torque. So how do we calculate angular momentum? To calculate angular momentum, we just use the formula. The angular momentum would just be the cross product of the moment on and the linear momentum. Now, this object is moving at the velocity, so there is a linear momentum. So you have the so if we just use the use this, you have your RP and then sine theta. That's just the equation, right? So and what is your P? So you have your R and your P is mv and then sine theta. Okay, so I'm just going to erase this one. So then this becomes your R. Your R has 3. And then your mass is 2, and then your V is 4. And then you have your sine of what is the angle between the moment arm, so which is if we draw an extension, that's your R here, okay, and the velocity. The velocity is right here, which is the directions of velocity is also the directions of linear momentum. So what is the angle between them? You can see that the angle between them would simply be from this point to that point. And this is a straight line, so this is 180 degrees. You're given theta 2. So your angle would just be 180 degrees, 180 degrees minus theta 2, and your theta 2 is 30. So this is basically you calculate sine of 150. So after you plug in the numbers, you should get a numerical value that is equal to 12, and the units for angular momentum is kilograms times meter square and then over the seconds. Okay, so this is a simple demonstration of how to calculate angular momentum utilizing this equation. So it's R cross P. This is the magnitude. What about direction? Because you're dealing with a cross product, the direction is always that you point your fingers in the direction of the first vector and sweep your finger toward the second. So your first vector is your R. So point your fingers in the in the direction of the first vector and sweep your finger toward the second. This is your V, so R cross V. So your thumb is pointing outward, which means that it is positive. And what does that mean? It means that, so we use this symbol to indicate that, that's a positive value that's pointing out of the whiteboard. So in other words, it is counterclockwise direction. Okay, so that's the directions of angular momentum, and this is the magnitude. What about torque? You do the same thing. Your torque is basically defined as R cross F. So we just need to have the radius and also the force, which are all given, and sine of the angle between them. So your R is 3, and your force is 2, and then your sine of, we'll just do this. Sine of the angle between the radius and the force is just theta 3, and your theta 3 is 30. So what you have here is that your torque, you should have 3, and then the unit is Newton times meters. Okay. What about direction? Again, point your fingers in the directions of R. Sweep your finger toward the second vector. So it is also pointing outward. So it is. So it's a positive value, and its direction is counterclockwise. Okay. So that's problem 26. All right. And then we're going to do problem 41. 2R. So all right, problem 41. Let's see. What is it about? 41. So this figure shows a rigid structure consisting of a circular hoop of radius r, and so the diameter is 2r, and mass m. So this has mass m, and a square made of 4 thin bars, each of length r and mass m. So you have this four. Let's see. So you have these 4 bars, and each has mass m. And this is the total mass of this hoop is just m. Okay? And the rigid structure rotates at a constant speed about a vertical axis with the period of rotation, that's 2.5 seconds. So your t here is 2.5 seconds. So with the information t, of course, you can calculate how fast it rotates, because omega is just simply 2 pi over t. Okay? And then you ask, let's see, assume that your R here, your R value is 0.5 meters, and the mass is 2 kilograms. So you're asked to find the rotation inertia about the axis of rotation. So you want to find the rotation inertia of this system and also the angular momentum. So you want to find I and omega. So how do we do that? How do we do this? Let's see. So if we look at this system consists of this hoop and also this this square. So it's going to whole thing is going to rotate at this at the period of 2.5 seconds. So the first thing we can do is that we need to calculate what is rotation inertia, because you're asked to calculate rotation inertia. We call this rotation inertia, that's called I1. And then for this, so what is our I1? So for I1, just from this thin hoop, we have so this is the center. So you can see that it is not rotating through the center. It is rotating at the edge of the hoop. So you have to calculate the rotation inertia about the center of mass, and then use the parallel axis theorem to account for when the axis is not through the center of the inertia. Okay, center of mass. So your I1 basically consists of 2 terms. One is the rotation inertia through the center of mass, and then plus when the axis is not through this, and there's a separation. The separation here is your R. So use a parallel axis theorem. That will be the mass of the object, and then times the vertical separation of these 2 axes. So that will be just R, and then square. Okay. Now what is ICOM? ICOM for the hoop. So the ICOM is 1/2 mr squared. Okay, so it's 1/2 mr squared. This is from when you have this that's rotating about the center of center of mass. So it's 1/2 mr squared, and then plus the additional term that's from the separation of the axis. That's your mr squared. So then your I1. Do I have the numerical value? So your I1 basically is just 3/2 mr squared. So we'll just leave it like that. So this is your I1 when it's rotating about this axis. Okay. Now let's look at this. We call for this one we call the I2. We have to actually separate into 4 components. So you have I2, you have your I3 for this one, and you have that's your I4. What about this? This one basically has no contribution to rotation inertia because it's right at the rotation axis. When you have the object that's right at the rotation axis, this thing do not rotate. If this thing bar does not rotate, if it doesn't rotate, which means that there's no rotation inertia, so you don't have to include that. So what is our net rotation inertia? That will be I1 plus I2 plus I3 and plus I4. So we can just write here. So you have your I1 plus I2 plus I3 and plus I4. Okay? And we already calculate our I1. So the question is, what is our I2? Now for I2, again, this is the mass. The mass of this bar is m, and the distance from this point to that point is r. So your I2 will have a value of the mass times the radius square. Okay, so this is just by definition when you have an object that's placed some distance away from a rotation axis, then that would be just mr squared. So your m2 is your I2 is equal to mr squared. Okay, what about your I3? Your I3 basically, you have the central mass. The central mass for the I3 is this. So the central axis is this. Okay, but then it's not rotating about this axis. It's actually rotating about that axis. So you have to use a parallel axis theorem as well. So you have your I3. That should be the central mass, and then plus this distance, the mass of the object, and times the separation. The separation is r over 2. So mass and then r over 2 squared. Okay. So what is the center mass for this thin bar? So center mass, if you treat that as a thin rod, the thin rod has the expression of 1/12 mass and then r squared. Okay. So basically, you're adding 1/12 mr squared and then plus the 1/4 mr squared. So this gives you 1/3 or mr squared. So in other words, for this thin rod, when it's rotating about this axis, and that will be the rotation inertia will be the sum of the rotation inertia through the central mass plus this mr squared. Okay, this m and then the separation squared. So the separation is r over 2. So you have this. So you can say that your I3 and I4, they are exactly the same configuration. So you can just say that I3 is equal to this, and that's using the same argument, you have your I4. So then we have all the all the I information. So we're ready to calculate our I's, because our I would just be I1, which is 3/2 mr squared, and then plus our I2, which is mr squared, and our I3 is 1/3 mr squared, and our I4 is 1/3 mr squared. So altogether, how many? Let's see. Altogether, what do we have? So altogether, we get 3.16 mr squared. And because mass and r are given, so you can just plug into that, to find the numerical value. So your m is, your m is 2, and your r is 0.5 squared. So after you do the calculation, your I total is 1.6 kilograms times meter squared. Okay, so this is basically how you calculate the rotation inertia of the system, because you have these two consist of different shapes. So they will each have its own rotation inertia, and then you want to calculate the rotation inertia about that axis, and then add them together as the total rotation inertia of the system. Okay, and then the next thing that you'll also find is that what is the angular momentum? To calculate angular momentum, because we already have our I, so we can actually just use another expression for angular momentum, which is angular momentum is equal to I omega. You have your I here, so we need to find what our omega is. Now omega, because we have our t, omega and t, they differ by this. So omega is equal to 2 pi over t. Now you have the t that's given, which is 2.5. So it becomes quite straightforward. So you have your rotation inertia, that's 1.6, and your omega is 2 pi, and then divided by 2.5. So after you do the calculation, so again, I'm just going to use this. So after you punch in the calculator, you should get a numerical value that gives you 4.02 kilograms per meter square per second. Okay? So that's basically the angular momentum. This is how you. So this is another expression for angular momentum. That's I omega, which comes very handy. Okay. All right. So that is that, and we're going to do problem 51. Let me erase this. All right, 51. A wheel is rotating freely at angular speed. That's 800 revolutions per minute. So this is your angular velocity. That's 800 revolutions per minute. On the shaft, whose rotation inertia is negligible, so I is negligible. A second wheel initially, so that's called W1. A second wheel initially at rest with twice the rotation inertia of the first is suddenly coupled to the same shaft. Although it says rotation inertia is negligible, let's say that it has rotation inertia I1 because the second wheel is twice the inertia of the first. So and the second initially has zero angular velocity, and with the rotation inertia that's 2 times the rotation inertia of the first, and then it's suddenly coupled together. What is the angular speed of the resultant combination of the shaft and the two wheels? So you also find what is the final angular velocity then. So this is when individually the first one has 800 is making 800 revolutions per minute and has I1, and the second is not moving, but it has the rotation inertia that's twice the magnitude of the first one, and then they couple together. What would be the final angular velocity? Because one is moving, so when you put added something on, the whole thing is still going to move. It's just that the angular velocity now would change because the conservation of angular momentum. Right? So the concept here is that the conservation of angular momentum. And so you'll also find what is the final angular velocity after these two move together, and how much energy is lost through this process. So that's first of all what we need to do is that we need to convert this into the SI unit. Okay, so let's do that. 51. So omega 1 is 800 revolution, which means that that's 2 pi radians, and then so that's in radians, and then per minute, so that's per second. So your omega 1, you should have a value that's 83.78 radians per second. So this is your omega 1, all right? And as we mentioned, the angular momentum is conserved. What does that mean? It means that initial angular momentum has to be equal to the final angular momentum, okay? And that's a conservation of the angular momentum. So in that case, the expression for angular momentum is, of course, is I omega. So it's I omega I is equal to IF omega F, okay? So let's see how many turns contribute to I omega. Initial velocity for the first one has this magnitude, so that's 83.78, and that's your I, we call that I1, okay? Now, the second wheel has no angular velocity, so there's no contribution. And once they couple together, the rotation inertia is, 2I plus 2I1 plus I1. And they move together as the final angular velocity. So from here, we can see that you get, this is your 3I1 omega, and this is just, you have this I1 get cancelled, so it doesn't really matter what the magnitude of I1 is. So your omega, the final angular velocity then becomes 27.9 radians per second. Okay? So we can see that going from 83 to 27.9 when you have two objects moving together. So there's a kinetic energy loss because it is not rotating as fast as when they are each individual turns. So let's calculate how much energy is lost. So let's say initial rotation kinetic energy would just be 1/2 I omega. So you have 1/2 I1 omega 1 square, and because there's the second wheel is not moving, so there's no contribution to the kinetic energy. So in this case, you can calculate that's 1/2 your I1, and your omega 1 is 83.78 squared. So that's your initial kinetic energy. After they couple together, we can calculate 1/2, and then your total I now is 3I1. and then your omega becomes 27.9, and you square it. Okay, so you have the initial kinetic energy and the final kinetic energy. So you can find the difference because you're asked what fraction of energy is lost, which means that Kf minus Ki, that's the loss of energy, over your Ki, the initial kinetic energy. That will be the fraction of energy that's lost through this process. So what we have here is that the difference between them. So what? Let's see. I calculate that. So your Ki. I actually calculate. So your Ki is equal to 3509.5 I1. And your Kf is, I calculate to be 1167.6 I1. And they are all expressed in terms of I1 because I1 is not given. So you can find the difference. So your final kinetic energy is 1167.6 I1, then minus 3509.5 I1, and then over initial kinetic energy, which is 3509.5 I1. So after you've done that, you see that your I1 basically doesn't matter because they canceled. So what we have here is that this one gives you negative 0.667. It is negative because energy is lost. How much energy has lost? It lost about 67% of the total energy. Okay, so that's basically based on the conservation of angular momentum, you can deduce how fast it moves after they change the rotational inertia.